So let's begin. Let's talk about how the cell works. So let's say that we have a zinc electrode on the left and a copper electrode on the right. Now, the standard reduction potentials for zinc and copper are as follows. This is the standard reduction potential for zinc, which has a voltage of negative 0.76. And here we have the standard reduction potential for copper, which has a voltage of positive 0.34. Now, in a voltaic cell or in a galvanic cell, cell energy is produced. The overall reaction is spontaneous, meaning that the cell potential has to be positive. In an electrolytic cell, you can use energy or put in energy to drive the reaction forward, so the cell potential doesn't have to be positive. It can be positive or negative. A good way to illustrate this is think of a battery. When the battery is powering your cell phone, it is using its own energy to do so, and so it's driving a spontaneous reaction. In that case, when the battery is powering your cell phone or laptop, it's acting as a voltaic cell or a galvanic cell. But when you plug in your battery into the outlet to charge it, well, energy flows from the outlet to the battery, and so it's behaving as an electrolytic cell because it's receiving energy from an outside source. So that illustration can help you to distinguish between a voltaic cell, which is a galvanic cell, versus an electrolytic cell. But what you want to take from this is that, remember, voltaic and galvanic cells, the cell potential has to be positive. It's going to be a spontaneous reaction. Now, here we have a voltaic cell because there's no outside energy source that's driving this system. So if the electrochemical cell is generating its own energy, it's a voltaic cell. Now, here we have standard reduction potentials. Anytime the electrons are on the left side, it's reduction. We need to switch one of these half reactions so that the overall cell potential is positive. If we switch the half reaction for copper, if we reverse it, the cell potential is going to change from positive to negative. And if we add the two, we're going to get a negative cell potential, which is what we don't want for a galvanic cell. So instead, we need to reverse the half reaction for zinc. Notice what happens when we do that. So the cell potential is going to change from being negative to positive. So it's positive 0.76 volts. And so at this point, we can add the two half reactions. If we add them, the electrons will cancel. On the left, we have zinc plus copper 2 plus, and on the right, we have zinc 2 plus and copper metal. So this is the net reaction. And the cell potential for this net reaction, all we need to do is add these two numbers. So 0.76 plus 0.34 is about 1.1 volts. So this is the standard cell potential for this particular reaction. Now, under standard conditions, the concentration of the ions, like the copper 2 plus and the zinc 2 plus ions that are in a solution, the concentration has to be 1 molar or 1 mole per liter. If the concentration is different, the cell potential won't be 1.1 volts. It's going to vary. It might be 1.08, it might be 1.15. It's going to change, but whenever you have a standard cell potential, that means that the concentration of the ions are also standard as well. It's 1 mole per liter. But now let's talk about how this reaction works. So looking at the first half reaction, this is an oxidation half reaction. The reason why it's oxidation is because zinc loses 2 electrons. It gives away 2 electrons. And notice that the oxidation state of zinc increases. It increases from 0 to 2 plus. So whenever the oxidation state goes up, or if electrons are lost, it's an oxidation half reaction. And anytime you see the electrons on the right side, it's also oxidation. Whenever the electrons are on the left side, it's reduction. the copper 2 plus ions are gaining 2 electrons, and so it's reduction. And if you look at the oxidation state for copper, it goes down from 2 to 0. So the oxidation number reduces or decreases, so therefore it's reduction. Now, let's understand what's happening in this electrochemical cell. So the zinc atoms in the zinc electrode are losing 2 electrons. So every atom is going to give away 2 electrons. And so the electron is going to flow from the zinc electrode into the copper electrode. So as zinc loses 2 electrons, it's going to enter the solution as zinc 2 plus. And as the electrons flow towards the copper electrode, the copper ions that are in the solution, well, they're attracted to those electrons. Opposites attract. And so those copper 2 plus ions, they're going to be pulled toward those electrons because there's an electrostatic interaction that pulls the electrons and the positively charged copper ions together. So they're going to accelerate towards this electrode. And so as the copper 2 plus ions picks up 2 electrodes, they're going to deposit themselves as copper atoms on this electrode. Now, the zinc electrode is called the anode, and the copper electrode is known as the cathode. Electrons always flow from anode to cathode. Also, oxidation always occurs at the anode. Zinc is being oxidized into zinc plus 2 as it gives away electrons, so oxidation is occurring at the anode. At the cathode, reduction occurs. Reduction always occurs at the cathode. You can see that the copper 2 plus ions are gaining electrons. Now, notice that the zinc electrode is losing mass. The zinc atoms are leaving the electrode and they're entering the solution. Therefore, the anode always it loses mass, so it gets smaller and smaller. Now the cathode, notice that it's gaining mass. The copper ions in a solution, they're depositing themselves towards the cathode, and so the cathode it gains mass. Now, let's talk about the salt bridge. First, let's clear away some space. So, let's say if you have 3 potential compounds to choose from. Let's say zinc sulfate, zinc hydroxide, and zinc carbonate. Which of these 3 compounds will be most suitable for the aqueous solution that contains the zinc electrode? Which one would you choose? The best one to use is the zinc sulfate solution. And the reason why that's the case is because zinc carbonate is insoluble. It's a solid. And the same is true for zinc hydroxide. So zinc sulfate is the best choice because it dissolves in water. It's aqueous. It's soluble. And so you want to use that. So we're going to use zinc sulfate and copper sulfate for both solutions. Now, the purpose of the salt bridge is to maintain charge balance. As the electrons flow from the anode to the cathode, ions are going to travel through the salt bridge. Now, it turns out that the zinc plus 2 cations, or the zinc 2 plus cations, they're going to move towards the cathode. Cations always travel towards the cathode. Cations are positively charged ions. The anions, like the sulfate ions, anions are negatively charged ions. And the anions, they travel towards the anode, so they move to the left. So make sure you remember that for this particular course. Cations travel towards the cathode. Anions, which are negatively charged, they travel towards the anode. So those are the basics behind the electrochemical cell. That's how it works. But now, let's go back to the reaction that we wrote before. The net reaction, which was zinc plus copper 2 plus, which turns into zinc 2 plus, and copper metal. zinc and copper are in a solid phase, and the ions are in an aqueous phase, which means that they're dissolved in water. So now, how can we identify which one is the oxidizing agent and which is the reducing agent? So in order to do that, you need to find a substance that is oxidized and a substance that is reduced first. So notice that zinc, the oxidation number increases from 0 to 2 plus. So therefore, we could say zinc was oxidized. And for the copper 2 plus ion, notice that the oxidation state decreased from 2 to 0. The oxidation state of any pure element in its natural state is 0. So because for copper it went down from 2 to 0, it was reduced. So reduction occurred at the copper 2 plus ion. The substance that is oxidized and reduced, it's always a reactant. It's always on the left side. So you can't pick one of the two products on the right side. It has to be on the left side. Now the substance that is oxidized is also known as the reducing agent. And the substance that is reduced is also known as the oxidizing agent. The reducing agent is the one that causes the other substance to be reduced. So zinc is considered to be the reducing agent because it causes copper 2 plus to be reduced. And the copper 2 plus is the oxidizing agent because it causes the other substance, zinc, to be oxidized. And so that's why you have to reverse them. So just so you know, metals are usually good reducing agents. And metal ions, sometimes they could be decent oxidizing agents. Nonmetals are usually oxidized agents like fluorine, oxygen gas. Those are oxidizing agents, by the way. So just want to make sure that you understand that particular concept. So we know that zinc is being oxidized to zinc 2 plus. So we're going to start with zinc solid. And then we're going to have a line. This line is going to separate the solid phase from the aqueous phase of zinc. And then we're going to have a double line for the salt bridge. So as you can see, the first half of the cell notation represents the oxidation part of the reaction. The second half is for the reduction. So we're going to start with copper 2 plus, which is also in the aqueous phase. And we're going to separate the aqueous phase with the solid phase. And so the second side, or the second part of the cell notation represents reduction. So that's one way in which you can write the cell notation for a reaction. A current of 1.25 amps passes through a solution of copper sulfate for 39 minutes. Calculate the mass of copper that was deposited on the cathode. So let's go over a few things. Q is equal to IT. Q represents the charge, and the charge is measured in coulombs. I represents the current, which is measured in amps, and T is the time in seconds. So what you need to know is that 1 coulomb is equal to 1 amp times 1 second. And the second thing you need to know is Faraday's constant. Faraday's constant is 96,485 coulombs per 1 mole of electron. Now, in the conversion, I'm not going to write coulombs. Instead, I'm going to use amps times seconds in place of coulombs. So let's go ahead and begin. So the first thing we need to do, we need to convert minutes into seconds. So there's 39 minutes. And in each minute, there are 60 seconds. So the units minutes cancel. And then we're going to multiply this by the number of amps. So we have 1.25 amps. So now that we have amps and seconds, we can convert that into moles of electrons. So there's 96,485 coulombs, or amps times seconds, per 1 mole of electrons. Now we need to convert moles of electrons into copper. And we need to understand the half reaction for copper 2 plus. So in copper sulfate, we have the copper 2 plus ions, and it's going to pick up 2 electrons in order to become copper metal. And when that happens, it can deposit itself on the cathode. Keep in mind, the mass of the cathode increases, the mass of the anode decreases. So notice the ratio between copper and electrons. It's a 1:2 ratio. So for every 2 moles of electrons that passes through the solution, we can say that 1 mole of copper will be deposited or plated onto the cathode. So now the last thing we need to do is convert moles into grams. So we need to reference the periodic table. And the atomic mass of copper is 63.55. So which means that there are 63.55 grams of copper per 1 mole of copper atoms. So let's focus on the units now. We see that the units seconds cancel, and the units amps cancel as well. And moles of electrons cancel, and moles of copper cancel. So we're left with grams of copper. So now all we need to do is the math. So 39 times 60 times 1.25 divided by 96,485 times 63.55 divided by 2 is about 0.963. So that's how many grams of copper were deposited onto the cathode. So the mass of the cathode increased by 0.963 grams. Number 2. The mass of the zinc anode decreased by 1.43 grams in 56 minutes. Calculate the average current that passed through the solution during this time period. Now, in the last example, we had the time in minutes and the amps, the current in amps, and we were able to calculate the mass in grams. Now we have the mass in grams and the time. We need to find the current. So let's start with 1.43 grams of the zinc anode. And let's convert it into moles. The molar mass of zinc, let me consult the periodic table, is about 65.39. So there are 65.39 grams of zinc per 1 mole of electrons. Actually, per 1 mole of zinc atoms. That's what I meant to write. Now we need to convert moles of zinc into moles of electrons. And for the zinc half reaction, because we're dealing with the anode, we know oxidation occurs at the anode. So it's going to be written this way. But the important thing is the molar ratio. And we can see that the molar ratio is 1:2. So that means that for every 1 mole of zinc that is displaced into the solution, 2 moles of electrons passes through the wire or through the solution. Well, technically, the electrons don't really pass through the solution. They travel through the wire. So I guess I should have rephrased this problem in a better way. It's the ions that actually passes through the solution, but the electrons, they travel from the anode through the wire to the cathode. So now let's use Faraday's constant to convert from moles of electrons into amps times second. So 1 mole of electrons is equal to 96,485 coulombs, but instead of writing coulombs, I'm going to write amps times seconds. Now this is the part where we want to pause and think about where we are right now. So the moles of zinc cancel and the moles of electrons cancel. Now we want to find the amps, so we need to divide by seconds. So let's convert 56 minutes into seconds. We know that all we need to do is multiply 56 by 60. So that's 3,360 seconds. So if you want to get amps, we need to divide by the time in seconds. So notice that the units seconds cancel, and so we're left with amps. And that's going to be the current that passes through the anode to the cathode by means of the wire. So 1.43 grams of zinc divided by 65.39 times 2 times 96,485 divided by 3360. So the current is 1.26 amps. And so that's the answer for this problem. Number 3. how long will it take in hours for a current of 745 milliamps to deposit 8.56 grams of chromium onto the cathode using a solution of chromium 3 chloride? So feel free to pause the video and try this problem yourself. By the way, if you want more examples, particularly multiple choice questions on chemistry, if you're preparing for like a final exam, check out two videos. One of the videos that I've created, General Chemistry 2 Study Guide Review, and there's another one on General Chemistry 1 Study Guide Review that I've created as well. So you can check that out, and it has a lot of multiple choice problems, and you can get more practice on these questions if that's what you're looking for. So let's go ahead and begin with this problem. So we're looking for time. Let's start with the mass. So there's 8.56 grams of chromium, and we need to convert it into moles. So the molar mass of chromium is 52. So 1 mole of chromium atoms has a mass of 52 grams. So the units grams cancel. And now we need to convert moles of chromium into moles of electrons. So let's write the half reaction for chromium. Notice that chromium is in the +3 oxidation state because there's 3 chloride ions attached to it, and each chloride ion has a charge of -1. So this is a reduction half reaction. So chromium +3 is going to need 3 electrons to turn into chromium metal. So the molar ratio is it's 1:3. So for every mole of chromium that is deposited onto the cathode, 3 moles of electrons passes from the anode to the cathode. So now the units moles of chromium cancel. So now we can convert moles of electrons into amps times seconds. So 1 mole of electron is equal to 96,485 amps times seconds. Now because we're looking for time, we want to cancel not the seconds but the amps. So what we have is a current in milliamps. 745 milliamps is the same as 0.745 amps. To convert from milliamps to amps, you need to divide by 1,000. 1 amp is equal to 1,000 milliamps. So we're going to divide by 0.745 amps. And so at this point, we have the unit in seconds. Moles of electrons cancel as well. So now we need to convert seconds into hours. So we know that there's 60 seconds in 1 minute, and there's also 60 minutes in 1 hour. So now this is going to give us the answer. So it's going to be 8.56 divided by 52 times 3 times 96,485 divided by 0.745 divided by 60 and divided by 60 again. So the answer that you should have is about 17.77 hours. That's how long it's going to take to deposit 8.56 grams of chromium if we use a small current of 0.745 amps.